Hello everyone, welcome to Code Guide. And today in this session we'll discuss the topic optimizer in neural network, and we'll start with the implementation part. So first of all, step one would be to install the required library. Install required library. Okay. So we'll install TensorFlow, Pandas, Pandas for data handling, scalar for preprocessing, and matplotlib, matplotlib for plotting the graph. You can say plotting the graph. So we'll install TensorFlow, and Pandas, then scikit-learn, then matplotlib. Okay. Now next we will import the required libraries. So next step is import the required libraries. Okay. First of all, we'll import pandas as PD. Okay. And what we are using this for loading and handling data. For loading and handling data. Okay. Then we have import numpy as np, and this is used for numerical operations. For numerical operations, then we import TensorFlow as TF, which is the main deep learning framework. And then we'll import matplotlib dot pyplot as plt. Okay, that is for plotting graph. For plotting graph. So also we can say for visualization purposes. Now we will move on with from sklearn dot model selection. We will import train test split. Okay, this is for splitting data into training and test set. For splitting data into train and test set. Okay. Now last one would be from sklearn dot preprocessing import standard scalar, which is used for normalizing featured values. Run this cell. Now third step is to load the dataset. Load dataset. Now I will use the URL. Okay, this is the URL for the dataset, and the URL for the Prima India diabetes dataset. Okay. Then as this dataset does not have any column name, okay, so we need to basically give manually the name. So column name for better readability. First of all, we'll mention the column name. First column name would be the pregnancies. Then next would be glucose. Now these are the important parameters which are used for when we are dealing with diabetes. These are the parameters which are measured often. Blood pressure. Okay, glucose, blood pressure. Then we have the skin thickness. Then we'll go for insulin, and we have BMI, that is the body mass index. and we have the diabetes pedigree function. Then we have the age. Now remember, these all are independent feature, and our last target variable is the output. Okay, these are column names. Now we'll give this column name to our data set. So for that, we'll mention the load the data set now. Load the data set into a data frame. Okay, df equal to pd dot read csv. We'll mention the URL here. Then the name equal to column name, and then we will show the first five rows. First five rows. When you run this, okay, I'm not mentioning df dot head by using df dot head, and I've not mentioned any value, so by default it is 5. So we got our 9 features, and one is the target. So 1, 2, 3, 4, 5, 6, 7, 8. These are the independent features, and this is our target variable. Now you can observe here, we have 1 and 0, only two values in the target variable. So this is a binary classification problem, and generally when all these values or parameters are high, we see that the person has got diabetes, and when these parameters are low, then we see the person does not have diabetes. So we have loaded the data set. Now next is we want to pre-process the data. Okay, so next step is pre-process pre-process the data. Okay. Now, first of all, we need to separate the feature. In X, I want to keep all the independent variables and in target label, and I want to keep the target variable in the Y. So, first of all, we'll mention separate separate the feature, separate feature as well. Feature X and target label, that is the Y. Okay. Next, I want all the independent features. So, df dot drop, I will drop the outcome which is the target variable. So naturally I will get the all that independent variable value, right? And then I'll mention x is equal to 1. Now these are the independent features. Independent features. Okay. And next we will have the target. So I'll mention the outcome. Now we have separated the feature. I'll mention this is a binary target variable. Target variable. Okay. Now we'll normalize the feature value to mean equal to 0 and standard deviation equal to 1. Next is normalize the feature values to mean equal to 0 and standard deviation equal to 1. Okay. For that we have scalar equal to, I'll mention the standard scalar, and I'll scale the x, that is the independent variable. So x scaled equal to scalar dot fit transform, and I'll mention the x. So what will happen here? It will scale feature to improve training performance. Scale feature to improve training performance. Okay. Now after scaling, we need to split it into training and testing data. So split into 80% training and 20% testing data. First of all, we mention the variable x train, comma x test, then y train, comma y test. Okay. I'll mention the train test split, and I'll mention the x scaled, comma y, comma test type. I'll mention 0.2 because I want 20% testing data and 80% training data. So that's why I kept the test size as 0.2. Then I have the random spread. So random spread will be 42. Okay, I'll run this cell. Now pre-processing is done. Now next we will create a simple neural network. Next step is create a simple neural network. this function return, or I'll say the below function will return a new model instance each time it's called. I will create the function. So def, I'll say create model, and that I will mention model is equal to tf dot keras dot sequential. Okay. First of all, I'll start with the hidden layer. So tf dot keras dot layer dot then first hidden layer background will be screen suppose. Okay. My activation will be relu. Okay, put here. Activation would be my relu, and the input layer neuron will be input shape equal to x train comma shape and 1. Okay, so this will give, if I print this, what will get? The total number of independent features, and that will be the number of neurons in the input there. So this is the x dot step 1, and this is my first hidden layer. Okay, this is my first hidden layer. Hidden layer. Now next, my second hidden layer. So here dot keras dot layer dot bench. Okay, and I'll mention here neuron suppose 8. I'll mention the activation function as the relu. So this is my second hidden layer. Okay, this is my second hidden layer. Now then I will have my third keyboard keras dot layer dot bench, and I have one sum activation equal to sigma. This is my output layer. Now in output layer, as it is a binary classification, so number of neurons will be 1, and for activation function for binary classification, we use it as sigmoid. So we gave it as sigmoid, and this is my output layer. Okay, and after this, I will return my model. Okay, now we created a simple neural network. Next would be define a training function. Next step is defining or define a training function. Okay, the nation training a model using a specific optimizer. I will create a function named as train model, and I will pass the optimizer name, and I will pass the optimizer, and here I will pass the epoch equal to, suppose I pass 50, right? And get the model equal to create model. This is the create model function. After that, I will which will create a model, basically create a fresh model for each optimizer. Create a fresh model for each optimizer. Now we'll compile the model with your optimizer. So compile the model with given optimizer and and loss function for binary classification. Okay, compile the model with given optimizer and loss function for binary classification. So we'll use model.compile, and I'll mention optimizer equal to optimizer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 1 optimizer equal to optimizer, and then I will mention the loss. As it is a binary classification, we'll use the binary cross entropy, and then we'll use the metric accuracy, which is basically track accuracy as a metric, Then we'll train the model silently for a few epochs. Next is train the model, silently for few epochs. So for that, I'll use history equal to model.fit, and I'll mention the explain from a y train, and I'll mention the epoch equal to epoch. Then I'll mention the batch size equal to 32. And then I will go with the verbose equal to 0. Now we will print the final training accuracy. So print, we'll mention the optimizer name, and then we'll mention the final accuracy. I'll mention history accuracy 1.4, and then we'll return the loss and accuracy values across all epochs. I'll mention return history. I'll mention the log comma history. I'll mention accuracy. Okay. Now we have defined a training function here. At last, we need to define the optimizer. We have defined a training function. Our next step is define a optimizer and train model. For that, we'll create a dictionary of optimizers to compare. So optimizer. First is SGD, that is the stochastic gradient descent. You know, guys, that when what SGD basically stands for, and we have discussed this in prior presentation. So for getting the SGD, we'll use TensorFlow dot keras dot optimizer, right, and dot SGD. Now here I'll mention the learning rate. Suppose I mention 0.01. Now this, keep in mind, this is the basic stochastic gradient descent. Okay. Now next is SGD plus momentum. OTF dot keras dot optimizer, right, and dot SGD. Here I'll mention the learning rate, which would be 0.01, and then I'll mention the momentum, which would be 0.9. Suppose we'll basically add momentum. Next we'll see the RMSprop. TF dot keras dot optimizer dot RMSprop, and here I'll mention the learning rate. 0.001, which is an adaptive optimizer. Adaptive optimizer. Next is Adam tf dot keras dot optimizer dot Adam, and here I'll mention the learning rate at 0.001, which is the most commonly used adaptive optimizer, which is RMS prop plus momentum. That is the Adam. Most commonly used adaptive optimizer. Okay. Now we'll create the dictionary to store training loss and accuracy. Dictionary to store training loss and accuracy. Okay. For that we'll create a losses and accuracy. Okay. These are two dictionaries to store training loss and accuracy. Then we will loop through each optimizer. Okay. Loop through each optimizer. We'll use each optimizer and we'll train the model. So for name, comma optimizer in optimizer dot item, we'll print training with name, and then okay, L log comma accuracy equal to train model, and we'll mention the name comma optimizer. Here we'll get the losses, and name equal to L, and accuracy name equal to H. Now this is used to save the log curve, and the below one is used to save the accuracy curve. Save the accuracy curve. Okay, we'll run this. First of all, it is training with stochastic gradient descent. So most accuracy we got was with 8GD plus momentum, and then we have the Adam. Okay, now we'll plot the result. Next step is plot the result. First of all, we'll plot log curve for each optimizer. For that, we'll use a plt dot figure, and I'll mention the fixed size. I'll mention 10 comma 4. Then for core loop, for name comma loss in losses dot item, plt dot plot, and loss comma label equal to name, plt dot title log per epoch, or plt dot x label epoch, and plt dot y label will mention log plt dot legend, and plt dot z mention go, and plt dot show. So we have got the log per epoch for each optimizer. Here we are going with the increasing epoch on the x-axis, and the log is increasing as per according to the y-axis. Now as per we see, starting from the epoch, we see that the lowest loss is what by the HDD plus momentum, which is denoted by orange. Then we have the Adam, then we have RMSprop, and then HDD. Okay, so this is the log curve which we got according to the epoch size, and as we know, as we see, as the number of epochs are increasing, the loss is also decreasing. So that is the most important factor. But after a certain point of time, after a 50 epoch, the loss will remain the same. So at the point of time, we need to stop the learning, or we need to use the parameter for avoiding overfitting issues like the early copy, which will naturally favor computation power or the resources. So that is the loss for epoch. Now next we'll see for the accuracy. Next is we'll plot accuracy curve for each optimizer. For each optimizer, we have PLT dot figure fixed size equal to 10 comma 4, and we'll loop it for name comma accuracy dot item. Okay, and we'll say PLT dot plot accuracy comma label equal to name. We'll make PLT dot title accuracy for epoch PLT dot x label epoch PLT dot y label. We have accuracy. Then PLT dot legend PLT dot grid Mason true, and PLT dot show see how the accuracy curve look. Okay, so accuracy is highest for HGD plus momentum naturally, as the lowest is log is lowest for the HGD plus momentum. So same will be for the accuracy. It will show the highest HGD plus momentum. This is the orange one. And we have the atom, right? As number of epochs are increasing, our accuracy is also increasing. So that is the accuracy curve for you guys. Now I hope you guys understood the different types of optimizers and their implementation. I want you guys to practice it with different data set. Now I've used the liabilities one. You can practice different data sets, famous data set, and see how we can get different results by changing the learning rate here, momentum, or by number of epochs, batch size, how changing the batch size would differ the result, by changing the loss or the metrics if you want, how the model will evaluate, by changing the number of neurons, the number of hidden layers we can change. So you can try and see how the model will or the neural network will work. Now we'll move towards the summary part. Last is the summary. So first of all, I'll mention here optimizer, and I'll mention the strategy, and I'll mention and the benefit. Okay. Now first is HDD. So what we do here is the vanilla strategy is for vanilla gradient descent, and it is simple but slow conversion. Right. Next is HDD plus momentum. It will add momentum term, and it reduces benefit. It reduces oscillation, and speeds up learning. Okay. Then we have RMSprop, which is basically the adaptive learning rate, which is good for noisy data. And then we have the Adam, which is RMS prop plus momentum, which is fast conversion, and it is widely used. So hope you guys understood the summary part here, what we have learned up till now, and practice more to get more hands on the different optimizers. And if you want to optimize it further, or the accuracy is not increasing because of the overfitting problem, we can better do the hyperparameter tuning using the Keras tuner, and we'll get the optimum result for that. Okay, so now I'll see you in the next section with the new topic. Till then, bye.